All right, let's begin. Unit 5, Introduction to Electronics. So first of all, let's define electronics. What does electronics mean? Uh, electronics mean it comprises physics, engineering, technology, and application that deal with the emission. What does emission mean? It is control and flow of electrons in vacuum and matter. Okay, it is the flow and control of electrons in the vacuum and matter. What does vacuum mean? You guys, can you tell me?
No gravity.
Yeah, there is nothing. Okay, there is no air, there is nothing. So vacuum means that. Okay, so but still there is going to be electron flows there. So electronics deal with such kind of things. Okay, comprises means like includes or consists of. Okay, comprises. So let's continue. So we have vacuum tube devices. There are a few vacuum tube devices that we are going to learn. Before that, let's just give some information about what we are going to do. So when a metal is heated up, there are electrons at the surface of the metal. When you heat the metal up, the electron is going to get faster. Some of the more energetic electrons are going to try to escape from the surface of the metal. Okay, like it looks like evaporation. Okay, it looks like evaporation. This effect is going to be known as thermionic emission. Thermionic emission is going to be, what is going to be thermionic emission? The escape of electrons from a heated metal surface. Okay, the surface must be metal. If surface is not metal, then the electrons are not going to escape from the surface, or it's not going to be thermionic emission. Okay, you are going to heat the metal, and the electrons over there are going to reach a high speed. When they reach that speed, they are going to escape from the metal surface. Yes, no. No, you rose your hand, I think.
Sorry.
Okay, no problem. Let's continue then. Okay, for thermionic emission, again, high temperature is required. If there is no high temperature, if temperature is not high enough, this is not going to happen. Thermionic emission is not going to happen. There should be high temperature. Okay, and this high temperature will cause electrons to escape from the surface of the metal. Okay. So thermionic emission provides a controllable supply of electrons in a vacuum. Okay, we are going to control the electrons in a vacuum. There is cathode ray oscilloscope. Let me show you that. This is a cathode ray oscilloscope. You see this at hospitals, right? This cathode ray oscilloscope. So this is an electronic equipment that provides visual image, electrical signals, and oscillations over here. As you see, these are called oscillations. Okay. Yeah, these parts are called oscillations. If it's straight line, we are going to say probably it's applied to X plates. If it's up and down, or if you see signals like this, we are going to learn about Y plates. So that means the voltage source is applied to Y plates. Okay, we are going to learn about it in a few minutes. Any questions so far? All right, let me just. Any questions so far you guys have? If you have it, just you can ask. Okay. So let's begin to vacuum tubes. So there are a few vacuum tubes that we are going to learn here. The first one is going to be thermionic diode. The thermionic diode. What is thermionic diode? First, let's define the diode. The name of diode refers to the fact the device has two electrodes, one anode and the other one is called cathode. One of them is positive part, the other one is negative part. The first thing that we are going to do for thermionic diode, the metal plate is going to be heated to emit electrons or to give out the electrons. This was done electrically, placing the cathode in front of what amounted electric heater. Let me show you the heater over here. This is the shape. This part is the heater part. Okay. The positive part of the thermionic diode, we call it anode. The negative part is called cathode. And as you see, electron flows from negative to positive. Okay. In order to operate this device, we are going to need like a few volts. It could be DC or AC voltage, okay? The voltage shouldn't be high. Operate this device. As you see over here, it's we have 6 volt AC. As you see, this symbol shows the AC part. So this 6 volt will operate this device. Okay, this is the first vacuum tube that we are going to learn, thermionic diode. The second one, let's move on. We are going to learn about cathode rays. Cathode rays are another type of the vacuum tubes. They are a beam of electrons moving through a vacuum at a high speed. They are produced by electron gun. What is an electron gun? Electron gun is a component producing beam of electrons moving through a vacuum at high speed. Okay, it should be at high speed. When we talk about cathode rays, they should be at high speed. If they are not at high speed, we're not going to be able to call them cathode rays. Okay. It's look like in the thermionic diode, we are going to release the electron by heating the surface of the metal. Okay, but this time we are going to need a high voltage. This voltage can reach as high as 5,000 volts. It's very high. Okay. Remember, for the thermionic diode, we just need a few volts, but here we are going to need high voltage. It should be like around as much as like 5,000 volt. Okay. So here, this is a cathode ray electron beam. Actually, you're going to see the cathode rays that moving through this. As you see, from negative to positive, there are 5,000 volt change of voltage, 5,000 volt. Here again, there is heater over here. There is here low voltage supply for heater. It can be like, again, 6 volt. Okay. And the electrons are going to move again from negative to positive part. And they're going to move through the vacuum over here. Okay. Any questions? All right, let's continue then. Let's continue so when we use this device, we are going to have some properties. The first one, the wave property, we are going to observe. The wave property, what does wave property means? You are not going to be able to identify the cathode rays if you observe the wave properties. You're not going to be able to see them. Okay, they are very fast. They can pass through the thin metal easily without disturbing it. That means it's not detectable easily. Okay. Particle property, on the other hand, they are very slow. They do not radiate like wave. They leave the surface at 90 degrees. They deflect by electric and magnetic field. If there is magnetic and electric field, you can observe particle property of the cathode rays. They can turn a wheel in a path of the ray, like they have that much energy, and they travel far slower than light. Okay, they travel far slower than light. And in addition to these two wave and particle properties, they start normally from the surface of the cathode. They produce fluorescence on certain substance which they fall. What does this mean? When they like fall on a screen, you are going to be able to see them. They produce ionization in the gas through which they pass, and lastly, they possess large amount of kinetic energy. Especially, you can see this large amount of kinetic energy when you try to observe a wave property, because they are faster than the particle properties. Okay. Remember, the kinetic energy depends on speed. So if they have high speed, they are going to have also high kinetic energy. Okay. So the third one, we are going to learn about the X-ray tube. The X-ray tube, you guys already know. For example, when you go to the hospital, if there is something wrong with your, like, let's say, hands, elbow, or your, like, if there is something wrong with your bones, you get an X-ray. Like you get an MRI. That MRI use the X-ray. X-rays over there. So for the X-ray, we need 100 kilowatts voltage. Okay, 100 kilowatt voltage we need. Just let me 1 second. Okay. All right, let's continue. So again, we need 100 kilowatts voltage, okay, in order to release the electrons and see the X-ray. See the X-rays over there. Okay. Mostly when you apply this 100 kilowatt voltage, most of the beams of the energy is going to be released as heat rather than X-ray. So the anode will get very hot. Let me show you the device over here. This is the anode part. Okay. It is going to get very hot because you're giving the anode 100,000 watt voltage. Okay. It's very high. It is higher than the that we learn about cathode rays, right? It is higher than that. It's like 20 times higher than that. So when you apply this, it is going to get very hot. So in order to protect the device, we use tungsten wire here. Okay. To protect the anode, we use the tungsten wire because tungsten wire has a very high melting point. If you use another like another metal over here, you're not going to be able to see any X-rays because this is going to be broken when it reaches 100,000 kilowatt. Okay, 100 kilowatt. Sorry, 100,000 volt. 100 kilovolt, 100,000 volt. Okay, that's why we use the tungsten wire over here to protect the device. Okay, because it has a high melting point. Again, there is a heater over here, as you see. All the vacuum tubes, they consist of a heater. Heater must be there, and anode and cathode part must be inside of the vacuum tubes. Okay. So the fourth one is cathode ray oscilloscope. This is a cathode ray oscilloscope over here, as you see. When you release the electrons are going to first pass through the Y plates. It is going to be like wave property here. And then when they pass the Y plates, they are going to also pass through the X plates. They're going to pass horizontally here. And at the end, when they reach the vacuum parts on the screen, they are going to show the signal over there. Okay. So the beam of electrons produced at the spot on the screen over here, as you see. So before reaching, it's going to pass through the Y plates and X plates. Again, we talk about it. When you see rapidly varying voltage, you can see the oscillation on the Y plates. Okay, this could be a microphone or AC power supply. Okay, you cannot apply the DC here. Why? Because when you apply the DC, you are not going to be able to see the change in voltage in the Y plates. Remember, DC means like it is direct current. It goes directly, and it's going to go through the X plate, but not Y plate. So it is not possible to apply the DC over here. It should be AC. Okay, alternating current. So direct current, again, electric current that flows in constant direction. Direct current. If you apply the direct current here, you're not going to observe anything over here. It's going to go straight. Okay, so that's why better to apply AC current over here. And the other term that we have to know actually, it's gain control. What is gain control? Adjusting the amount of beam deflection in cathode ray oscilloscope is called gain control. Adjusting the amount of beam deflection. Let's say you say the beam are going to deflect by 5 centimeter. So gain control will arrange that, and it's going to show you the deflection by 5 centimeters. Okay. So some of the use of cathode ray oscilloscope, let's learn about it. The first one, direct current. When you apply the cathode ray oscilloscope to direct current, you're going to see a stationary spot on the screen like this. Here on the shape you see as a dot. So this is going to show the direct current applied on the screen. Okay. The second one is sensitivity. What does sensitivity means? The size of the deflection caused by voltage applied across Y plates of cathode ray oscilloscope is called sensitivity. We are going to use gain control to adjust the amount. Okay. For example, there is an example over here. Let's say this is the origin, right? This is the origin, this part. If you see, like I am showing with using mouse. If there is a deflection, and if it's like 3 volt over here, and if each square represented by 2 centimeter, over here, when you look for the peak voltage, it is deflected by what do you see over here? It's 2 squares. So each square represents 3 volt. So if it deflected by 2 square, the peak voltage is going to be 6 volt. So like when I sent you the note, I told you to check the word example 5.1. It's at page 151. Let me show you there also. Just a second. So just a second. All right, here there is an example. A 1.5 volt cell is connected to the Y plates of a cathode ray, and the gain control adjusted so that trace is 1 centimeter. What does it mean? It means when it moves by 1 square, it's going to deflect by 1 centimeter. Okay. The cell is removed and an unknown potential difference applied to the Y plates, and the new trace is seen on the screen of the cathode ray here, over here. What is the size of the unknown PD? As you see, for each square, it represents by 1.5, right? So here is 1.5. If it deflected 2, then it is going to be, our unknown voltage will be 3 volt, okay? So deflection will be 2 centimeter. You are going to multiply by 1.5, and that is going to give us 3 volt deflection over here. For each square is 1.5, so for 2 square is going to be 3. For third one is going to be 4.5. For fourth one is going to be 6. It can go up and down, okay? Or right and left, doesn't matter. For the Y plates. Any questions? All right, let's continue then. That was the example. So time base, there is time base also. Let me show you. This is one time base is off. You are going to see a dot because it is going to be applied on X plates, okay? When there is time base, we are going to apply the voltage supply to the X plates. And on the X plate, you can see a dot if it's off time base. And when you turn on the time base, you are going to see that the line is going to move to the right and left horizontally. It's not going to move vertically, okay? It is going to be horizontally because you are applying the voltage to the X plates. If you apply voltage to Y plates, you are going to see deflection as, let me show you here. You are going to see the deflection as sine wave, like this, okay? You're going to see this deflection when you apply to Y plates. So here, there is an example. If it's like, if we adjust our time base 1 millisecond per centimeter, so it's going to take 1 millisecond to move 1 centimeter to the right or to the left, okay? So what we see on the screen is going to be input voltage plotted against time. Input voltage plotted against time. This is going to be what we are going to see, okay? There is a question, I think. Okay, no problem. Let's go. Continue. Okay. The other application of cathode ray oscilloscope is alternating current. Again, if there is alternating current, you are going to see the wave property of the cathode ray, okay? Here, when the time base is off, you are going to see this line on the screen. And when you turn on the time base, since you are going to apply the voltage to the Y plates, you are going to see a sine wave over here. So the oscillation will happen over here, and you're going to see this when the time base is on. What is a sine wave? It is a mathematical function that describes a smooth, repetitive oscillation. The distance between two are going to be equal all the time. So it is repetitive. They repeat themselves. These waves are going to repeat themselves. And we are going to call them sine wave, okay? So how do we find the period and frequency by using alternating currents or voltage using cathode ray oscilloscope? Here, for example, let's go back. We are going to find the frequency and the period by applying alternating current. So to find the frequency or period, we are going to use this formula. 1 over frequency will give us period, or 1 over period will give us frequency. The SI unit of period again is second, and the SI unit of frequency will be 1 over second, okay? So there is an example over here. Let's do this example actually. So let's move forward. I can write on it. So all right. So let's try to given what we have here. So as you see, the sensitivity of cathode ray oscilloscope is set to as 7 centimeter per second. What does it mean? It means per 1 centimeter is going to be 7 centimeter deflection, okay, to the right. And the time base is setting to 1 millisecond per centimeter, 1 millisecond per centimeter. What does it mean? It means like when it goes on the right, it's going to be 1 millisecond per centimeter. Find the peak voltage and the frequency of the AC signal shown in the figure. Okay, so to find the peak voltage, we are going to count from the origin, this is the origin line, to the top of the, what do you say? To the top of the wave, okay? So how many square do we have here? 1, 2, and 3. Since we have 3 square, we are going to say 3 times, sorry, 3 times, and our voltage set to by 7 centimeters, 7 voltage, right? So we are going to multiply by 7, and we are going to get 21 volt peak voltage, okay? You are going to count from, you are going to count vertically, okay? From origin to top of the wave. How many square you have? 1, 2, 3. So you're going to say 3 times 7 centimeter per second, 7 voltage per centimeter. When you multiply it, you're going to get 21 volt peak voltage. So it says like 1 millisecond per centimeter, right? So since you have 21 volt, that means you're going to have, let's count over here, how many, what is the distance between peak 1 to peak 2? How many dot we have? 1, 2, 3, 4, 5. We have 5 squares between them. So that means our time base is going to be 5 millisecond. What does this mean? This means it's going to be 5 times 10 power negative. Let me see if we have negativity over here. 5 times 10 power, and cannot negativity. Okay, 5 times 10 power. Let's put it here, 10 power. Okay, 10 power negative 3. Okay, 10 power negative 3. So to find the frequency or period of the object, what are we gonna do? This is our what? Since this is second, this is going to be our period. So to find the frequency, what we are going to do? Frequency equal 1 over period. So that's going to be 1 over 5 times 10 power negative 3. So that means the frequency for this device is going to be, when you divide 1 to 5, 1 over 5 power 5 times 10 power negative 3, you're going to get the frequency as 200 each, 200 per second. Okay, 200 per second will be our frequency. 200 per second, or 200 over 1 over second. That is going to be the frequency of the oscilloscope. Okay, so did you understand, guys? For the frequency, you're going to count from left to right between 2 peak points. How many, how many square you have? You are going to count them. Each square represents 1 centimeter again. So for 1 millisecond per centimeter, since there are 5 spots difference between these two, you are going to say 5 millisecond. Okay, and you're going to find the frequency like that, 1 over period. To find the peak voltage, you are going to count from down to up, from the origin to the peak point of the wave. Okay, so since we have 1, 2, 3, and you're going to multiply the what is given to you over here, 7 volt per centimeter. When you multiply it, you're going to get 21 volt peak voltage. Okay, up to down to find the peak voltage, left to right to find the frequency of the device. Okay, any questions? Let me see, there's nothing, I think. All right, let's move on. If you have questions, like you can write on the chat button at the top. You can see chat button, so you can write there too. Okay, if you don't want to talk. All right. So you have a homework, page 163. I want you to do that, guys, and we are going to. If you have any questions, you can send it to me. I can solve it to you on Telegram. Like, doesn't matter. On Tuesday, I'm going to check. I'm going to ask you questions about it. So Tuesday we can go over it as well. Okay. So we are about to finish the lesson. We have 5 minutes. Let's just finish these two parts, and then we are going to finish today. Okay. So conductors, semiconductor, and insulators. You guys know already about conductor and insulators. Remember, insulators does not allow the electrons, or like does not allow the conductivity, but conductors such as metals, they allow the electrons pass through them. Okay. So what is the reason? Because there are many free electrons moving inside of the metal. That's why they allow the conduction for the conductors part. And we have the new terms you are going to learn: semiconductors. What does semiconductors means? They don't have enough energy. They're outmost part of the shell. Okay. When when you heat the metals, the number of the electrons at the top part will increase. For example, silicon, germanium, lead sulfide, selenium, and gallium arsenide are all semiconductors. You know them from periodic table, right? You know these metals from the periodic table. These elements: silicon, germanium, lead sulfide, selenium, and gallium arsenide. These are all semiconductors. Okay. So we have intrinsic semiconductor and let's see chat part. Unfortunately, we don't have time to do it because it's like the meeting arranged automatically by Squad. So I'm going to post the video. You can check it out later, okay? Because we have just 3 minutes. After 3 minutes, it's going to like shut itself down. The meeting arranged to 30 minutes. That's why. Okay. So we have intrinsic semiconductors, and we are going to learn later on extrinsic semiconductors. So intrinsic semiconductors, they are pure semiconductors. They do not contain anything inside. We call them dopant. Dopant. If there is dopant inside of the semiconductors, it is going to break the impurity inside purity inside of the semiconductors. Okay, so that's why there is no dopant. What does dopant mean? Dopant means like from outside you give an electron to the conductors. Okay, so it's going when you give an electron from outside, you are going to dope the semiconductors, and you're going to make this one an intrinsic semiconductors. Okay, so their conductivity is not affected by external factors. Whatever you do, you give them, like, let's say heat, you give them something else, this is not going to affect their conductivity. Intrinsic conduction, there are electrons and holes. Holes represent the positive parts, electrons represent negative ones. They move in opposite directions when you apply an EMF, okay? A voltage, when you apply them, you are going to see that electrons and holes are going to move in opposite directions. So to find the total amount of current, we are going to use the current of electrons and current of holes to get the total current of the intrinsic semiconductors. Okay. Here, when you see this shape, you are going to see that when you apply a voltage source over here, the holes, these are the positive ones, and the electrons are going to move in opposite directions. Okay. As you see, electron goes to right, but protons or the holes are moving towards left side. Okay. This is only going to happen when you apply an EMF. Okay. When you apply a voltage. When you apply voltage, the electrons are going to move towards the right side, and the protons or the holes are going to move towards left sides. We are going to call the positive ones p-type semiconductors, and we are going to call the negative ones n-type semiconductors. So you have another assignment, review questions at page 166. You can do the question again. If you have any questions, you can just text me, or you can just call me. I can explain to you, no problem. Okay. So let's finish here. Let's finish here because we are already done. Okay. We in our next lesson, we are going to cover the second portion of the. Let's just stop the recording.